Hey Georgie, I bet your handsome self can't find where Captain Lopital went.
Nonsense, silly. He was filled up with lead bullets at the Battle of Riemann. I saw it with mine own eyes.
I can't believe it. That jolly chap was so sweet. Even sweeter than that concoction you derived for me yesterday eve.
I swear 'tis true. On my honor. I saw him fill up with lead bullets until he was like a giant sphere.
Oh my.
Indeed. He rolled over the limits and into the Pythagoreans.
Well, how big did he get, love?
Well, I don't know, 'cause he reached the limit of his skin and flew in all directions with a velocity of infinity. Charles Dodson guesstimated by his parts strewn about that he did get rather large.
Well, how fast was his stomach getting fatter like Howard Taft fool?
Silence. Taking into account the fact that lead bullets have a diameter of 3.14 centimeters, he would grow with bullets proportionally to the rate at which he is hit by bullets. My best scientist, Euler, fathomed that his stomach must have been increasing in volume 20 cubic feet per minute.
That's jolly terrible. My secret lover told me that the volume of a sphere is 3/4 pi r cubed.
Wrong. That would be 4/3 pi r cubed. Jolly joker. I bet you don't know what to do after this. Maria Agnesa taught me how to do it.
Oh, fie. I know. We take the implicit derivative of the volume equation with respect to time.
Huh? You don't even have any respect for me. How are you going to have it for time?
Oh hush, sweetie pumpkins. I measured him myself yesterday for his battle suit. I know for a fact that his waistline is 12.56 feet. Therefore, using the most simple of equations, 2 pi r, he had a radius of 2 feet.
Okay, well we know then, thanks to Euler, that he increased at a rate of 20 cubic feet per minute, and due to your scandalous love affairs that he had an initial radius of 2 feet.
Well, I never.
We have the rate at which his volume changes with respect to time, and we need to find the rate at which his radius changes with respect to time.
Oh, I know. Take the derivative. Take the derivative. Take the derivative.
Oh yes. Euler told me this. If I simply take the derivative of the volume equation, then the result is how quickly a sphere's volume changes with respect to time.
And if we take the implicit derivative to find the rate at which the volume changes, then we have 4 pi and a squared off radius times the rate at which the radius changes.
Indeed, if by that you mean 4 pi r squared times the change in radius with respect to time. Aha! We know the rate at which the volume changes and his radius, so we can use that to solve for the rate at which his radius changes.
Georgie.
So we can set 20 feet cubed per minute equal to 4 pi times 2 squared times dr over dt.
Georgie.
And Euler said just get the dr over dt by itself. So we get 20 equals 16 pi dr over dt. Then we divide by 16 pi.
Georgie.
And when we reduce, we find that it is 5 over 4 pi feet per minute equal to dr over dt.
Georgie, Georgie, Georgie.
So that's it. His radius is increasing 5/4 of a pi per minute. Ha. Oh, yes dear.
So what you do is 1. Assess what data you had. 2. Find the appropriate equation for the evaluated shape. 3. Find the implicit derivative of said equation. 4. Plug in the data that you already know and solve for what you wish.
Why yes dear. You are such a charmer.